Hi, this is Moser with a quick tutorial on ionic compounds, when opposites attract. After you've watched this video, you should be able to describe ionic compounds as the result of attraction between large numbers of cations on anions, identify the crystal lattice as the structure which is formed by ionic compounds, as well as distinguishing the properties of ionic and molecular compounds and explaining what atomic behavior causes these properties. So coming into this, you should already know what cations and anions are and the basics of what causes ionic versus covalent bonding. Hey, you remember this chart, right? Looking at electronegativity difference, and you know that any time that an atom of two elements have a electronegativity difference greater than 1.7, one of them will tend to give up an electron, boop, and the other will tend to gain an electron, causing us to have a cation, a positively charged ion, and an anion, which are irresistibly drawn to sit shoulder to shoulder. They're not sharing electrons, they've actually traded, and now they're being bound by a very powerful force of electromagnetic attraction. Yeah, that sounds about right. So once we've had something bond ionically, we have an ionic compound. And ionic compounds are made of positive and negative ions, combined so that the charges that are positive and the charges that are negative balance out. In other words, we have a ratio that when we multiply out gets us an overall neutral effect. Most ionic compounds exist as crystalline solids, and you've seen many of these. You've probably seen table salt. Here it is in the form that it's mined out of the earth, and notice that it's just big old crystals. Well, that's how most ionic compounds exist. So if you remember that with compounds that are bound covalently, we have molecules and molecular formulas. With ionic compounds, the chemical formulas are actually what's called a formula unit, because there are no molecules in an ionic compound. What? That's right, no molecules whatsoever. A chunk of salt is a huge collection of sodium and chlorine ions, each attracted to one another. So there's no one discrete unit. It's a big, massive attraction. Crazy, huh? The formula unit is the simplest collection of ions that establishes the ionic compound. And the ratio of those ions all depends on the charge on each ion. Well, with sodium and chlorine, it's easy. Sodium's a 1 plus, chlorine's a 1 minus, so one sodium will balance one chlorine, giving us an overall neutral effect. With calcium and fluoride ions, calcium has a 2 plus charge and fluoride has a 1 plus charge. So it takes 2 fluoride ions for every 1 calcium ion to have an overall neutral effect. We'll spend lots more time on this when we talk about naming and formula writing, but just as sort of a little exercise, what ratio of aluminum to oxide ions would you expect to see? Aluminum has a 3 plus charge, and oxide ions have a 2 minus charge. So, if we have 2 aluminum ions, that gives us a plus 6, and 3 oxide ions gives us a minus 6. So that would balance out. The formula for aluminum oxide just happens to be Al2O3. Like I said, we'll talk more about that when we get to formula writing. Lewis dot diagrams are really handy for showing the transfer of electrons and the formation of ions. Here we have the Lewis dot diagram for chlorine and the Lewis dot diagram for sodium. When sodium gives up its electron and chlorine gains an electron, we show them like this. And if you recall, when we do a Lewis dot diagram or a Lewis structure for an ion, we always show a bracket with the charge. So we can see that chlorine's gained an electron, we can see that sodium's lost an electron. Now, to show the formation of the compound, we just show the two of them sitting there, shoulder to shoulder. Note that they're not sharing any electrons. They're just sitting there, powerfully attracted by the opposite electrical charge. Because of this powerful charge of positive for negative ions, ionic compounds form crystal lattices Think of it as a big scaffolding with little atoms at every point. This is done to minimize potential energy. Remember that across all of chemistry, we see this theme that lower energy means stability. And so all compounds form to minimize potential energy. The positive and negative charges, the cations and anions, are spaced out evenly, sort of being held in the pull of the opposite ions near them and in the repulsion field of the same charge ions near them. Now, because this structure isn't one where two atoms are sharing electrons, it's just based on this balanced attraction and repulsion from a large number of cations, we can't calculate bond energy in the same way we do. With covalent compounds, we look at the bond energy contained in a single molecule, but there are no molecules in ionic compounds. So instead, we look at what's called lattice energy. If we take a mole of sodium ions, Na1+, and a mole of chloride anions, Cl1-, and we combine them, the amount of energy that's released when that mole of salt is formed from those gases is the lattice energy of sodium chloride. It's kind of weird and not something that we deal with a whole lot at this level of chemistry, but you should be aware of it. So there are some serious differences between molecular and ionic compounds. In a molecular compound, the bonds inside the molecule are incredibly strong, but the bonds between the molecules, those aren't so strong typically. Here are some sugar molecules. Well, okay, it's glucose, and yes, they're badly drawn, but they'll do. This outer purple line defines the boundary of each molecule. Again, in a molecular compound, we have these discrete units, and it's really hard. It takes a lot of energy to break the bonds within that molecule. However, getting one molecule to move away from the rest, well, that's not so hard, because the bonds that are formed between the individual molecules aren't all that strong. So you can start to get these to move apart without all that much energy. In an ionic compound, however, there is no molecular boundary. There is no discrete unit. It's just a big collection of cations and anions. And every single cation in this chunk of salt is pulling towards it every anion. And every anion is pulling towards it every cation. So the forces of attraction go in very much straight lines. Now there are, of course, forces of repulsion too. And that's why these things are keeping one another at a very safe distance, as close as the attraction will allow, or as close as they can get based on the attraction, but only as close as the repulsive forces between the like charges will allow. Because of this, ionic compounds tend to have much higher melting points and boiling points. You can take sugar, and you can melt it, well, with a candle. Keep that in mind. Salt, on the other hand, melts at something like 800 degrees Celsius. It's crazy. This is because of those attractive forces within the ionic solid. Molecular forces just don't have that. Ionic compounds also tend to be hard, but they're very, very brittle. There's a good reason for that. We've got our ionic solid here, and it's nicely lined up. All of our little positives and negatives in a perfect line, as close as they can get to the oppositely charged anions, and as far away as they can get from the same charged anions, holding together very, very tightly. But if we hit this with a hammer, boom, and exert some force straight down on it, what happens is that all of those bonds of attraction shift. Well, now, instead of bonds of attraction between part of this and the other part, we actually have a repulsive force. And what tends to happen is that when hit with hammers, for instance, ionic compounds tend to split or cleave along very regular lines. This is really important to geologists where they use those characteristics to identify the underlying minerals they're working with. Ionic compounds also tend to dissolve easily in water, and they tend to be quite conductive when they're dissolved in water or when they've been melted. The reason is, when we take an ionic solid and put it into water, you got to remember that water is a polar compound. That means that though water is covalently bound, there are areas of partial charge on the end of each water molecule. Because of these little regions of partial charge, water is very able to infiltrate into an ionic compound, snaking its way through this little forest of positive and negative charges, and actually teasing out those positive and negative charges, with the positive charges being attracted to the slightly negatively charged end of the water, and the negative charges, the anions, being slightly attracted to the positive ends of the water. It does a great job at dissolving ionic solids. It also means that once they've been dissolved, you have a sea, a wonderful, wonderful bath full of ions. And those ions mean that there are electrons that are free to move. That's what makes the solution conduct electricity so nicely. Okay, can you describe ionic compounds as the result of attraction between giant numbers of cations and anions? Identify the crystal lattice as the structure they form, and distinguish the properties of ionic and molecular compounds and why we see those? Good, then that's it. Keep going.